Hello students, my name is Shashank Shekhar and today is the sixth day of the chapter Chemical Kinetics. So if we have seen zero order reaction in the previous class, today we will be seeing the first order reaction. Okay, so we will first derive its rate law and again we will see some examples related to it. So let us start our today's class. So if I talk about the syllabus, so we have covered up till this part, that is the zero order reaction. Yeah, still we have not seen the half-life. I will cover this part wholly for both zero and first order in one time in the second lecture, or you can say in the next lecture. Okay, so today we will only cover the first order kinetics. We will see the graph related to it and what are the equations that can be formed, the integrated rate law equations. Okay, so we will see this. Now, if I talk about today's topic in more detailed fashion, so that would give us first of all what is a first order reaction and how can we derive its integrated first law. After that we will see an alternative way. So why I am introducing this alternative way. So the answer would be that it is a kind of general way of getting our final equation rather than following two different methodology which varies in the short which have a short variation between both of these, but still to follow a general algorithm would be more easier rather than to remember two types of procedure. Okay, so we will use that same method which we have used for the zero order reaction, that is using the limits while integration, and then we will find the integrated rate law. Okay, after this we will see what is the graph. What does the graph looks like? So we will have two graphs primarily, and we will see a special type of reaction which follows first order, that is the gas phase one. At last we will see some examples. So these are the today's topic that we will cover. So first of all, let us start with this first order reaction. What is first order reaction? So in first order reaction, the rate of the reaction is proportional to the first power of the concentration. So if I write it in terms of a common reaction, suppose we have a reaction in which reactant is going to product and we have coefficient 1 for both of this reactant and product, then in that case we can write that okay, rate is equals to minus dr by dt is equals to kr. Now this is the differential rate form. This is the differential rate form for the first order reaction, where the rate, that is this one, is equals to k times, means you can say rate constant times the concentration of reactant raised to the power 1. Nothing is written here, means it is 1. Then further we are just rearranging to get our coefficient in proper manner. So I have told to follow the algorithm, we will follow it here also. First we will write this, say our differential rate equation, then we will arrange our coefficients. So we are interested first of all in this part. So talking about this part, you can see that the rate is directly proportional to our concentration of reactant. Okay, now what are we doing? We are plotting a graph of rate against time. Now we know that with the passage of time, this concentration of reactant will decrease. Okay, this concentration of reactant will decrease. So this is the thing, right? Now what are we doing? We are taking different initial concentration. Okay, we are taking different initial concentration. So as we are changing the initial concentration in the increasing fashion, suppose we are taking 5 data points. Okay, we are taking 5 data points at different times, R1, R2, R3, R4. So it should be not time, it should be concentration here, or you can say more appropriately initial concentration or concentration simply. So this should not be here. So if we go on increasing the concentration, then we will see that the rate will also increase. Suppose R1 is less than R2, is less than R3, then is less than R4. Then the 4 rates will be here. Let me denote it with a different pen. Then this one will be here, 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 and here, where this is for R4, this is for R3, R2, and R1. Okay. So we can plot a graph like this, and this graph is very important. So if you have a concentration, rate again concentration, then we will get this graph. And this is our differential rate equation. So I want to make sure that you remember the graphs. The graphs are the most important part of this whole chemical kinetics, because you can predict, means you can just simply look at the graph and you can predict the order of this reaction that you are dealing with. So it's important to know about the graph. Now if you are asked that how did you get a straight graph like this, simply compare your equation with this. Y is equals to mx plus c, where we have rate is equals to kr. Now since I think this would go here, right? This would go here. No. Okay, correct. Yes. So we have y is equals to mx plus c. So y is the rate here, k is the slope, x is our reactant concentration, and c is equals to 0. This is 0. So we will get it as y is equals to mx. Therefore, since the intercept is 0, so the graph is starting from the origin. If some amount of intercept was present there, then graph would have started from here or either here or either here. Okay, but since all of this, say, intercept is equals to 0 here, since we have this plus c missing, therefore we will have a kind of a slope that will start or originate from the origin. Okay, so this is clear. So we have seen a straight graph for this y is equals to mx, and we have got our differential rate law, which we have seen earlier also. So the differential rate law goes like this: minus dr by dt is equals to kr. Further rearranging the coefficient, we get this. Keep this equation in mind. Okay, now we'll try to derive this rate law for the first order reaction. So we have seen this equation. We'll again consider that reaction only, in which reaction was going to product, reactant was going to product. Again, rate is equals to minus dr by dt kr. Rearranging this coefficient, we get this thing. So how we have rearranged it? See it carefully. So we have brought this r here, so that this dr and r can be on the same side, so that we can integrate properly. Again, there is no t term, but there is a k. So we just have to move this dt here. Now you must see this thing often, that we are just keeping dt along with k. So this is a common type of method you should follow. Okay, and rest you know what where the coefficient will go where. Okay, now we'll integrate it both sides. So that would give us ln r, and this k dt would give us kt plus I, that is the integration constant. Now how do we get this ln r? For those who are not aware about this, so this is a form of integration, that if we have dx by x, then it will give you ln x. So we have simply used this formula. Here we have r instead of x, therefore we are getting ln r instead of ln x. Again here we have the integration constant, that is I. So in NCERT book, what do? They try to find this integration constant by taking time t is equals to 0. So the same thing has been followed here also. So what we will do, we will try to take this as 0. Now if you remember my algorithm, which I have introduced, so we have just integrated using limits. So that is a kind of you can say a bypass in which we don't have to find about this. You have to get worry about this integration constant, because in finite integration, means integration with finite limits, they do not have any such kind of compulsions that we have to introduce I, because I is addressing for the constant that must have been erased due to differentiation, because differentiation of a constant is 0. But with the introduction of these limits, this thing is also managed. So therefore, introducing the limits and then integrating would give a more appropriate answer and quick answer, right? So if we look upon this equation which we have got, what we have to find now? We have to find I, this I. So how can we find it? So let us see. So we will assume that at time t is equals to 0, we have the concentration of R as R naught. That is the initial concentration. So t is equals to 0 is of course the initial time. Initial means starting time, and starting time we have taken as 0, and the concentration at the starting time is taken as R naught. So R naught here is the initial concentration. Now putting all those values here, which was there in the equation, ln R is equals to minus kt into plus 0. So ln R we have replaced by R naught, okay, and t we have replaced it with 0. After putting all these values, we will get I is equals to ln R. I is equals to ln R. So this is our value of I. Now we'll substitute this value in the equation. Sorry for writing here. Okay, we will just insert this I with ln R naught, right? Now just we have to make equation more easier to remember. So to do that, what we are doing, we are rearranging it. What we are doing, we are rearranging it. We are writing it as ln R by R naught is equals to minus kt. How is it happening? So simple. Just what we have to do, bring this ln R naught here. So for those who are unaware about the logarithmic property, it would give us minus kt, yes. And if you are unaware about it, you can just use this formula where it says that ln A minus ln B is equals to ln A by B. So similarly, ln R minus ln R naught is equals to ln R by R naught is equals to minus kt. Same equation is written here, okay. Now we will bring this t here along with this minus. Now you would ask that where is that minus gone? Where has that minus gone? So for those who don't know, ln A is equals to minus ln of A. So what is the value of A here? It's R by R naught. 1 by A. Okay. So if you put this value here, minus ln R naught. Okay, so we can write it like this, no problem. Now how do we get to this point? So very simple to understand, that a general property which says that A into ln B is equals to ln B to the power A, B to the power A, only B to the power A. So since minus, so if we take minus here, minus ln B, then that would give us ln n B to the power minus 1, and minus 1 means 1 by B. So we have done similarly here also. So we have brought this sign, minus sign here, that would change the reciprocal or reverse the reciprocal. So k is equals to 1 by t. T also goes here, 1 by t ln R naught by R. So finally we got this equation. Okay, so this is equation. This is the final equation. Of course you can simply simplify it furthermore, but for now this is our prime and the foremost integrated first law. This you should remember this, it's very important. If you don't remember this, at least remember some key points of this derivation, so that in case you forgot this all, you can just remember. So in case you forgot this all, you can just remember using your derivation. Okay, if you remember some parts of derivation, you can quickly get up to your answer. So if you remember, say our alternative method also, so that would be more easier. Just take the limit and do so. That would be more easier to calculate. Further, what we are doing, we are taking this at 2 time intervals. Okay, at time t1 we are saying the concentration is R1, and at time t2 the concentration is R2. Okay, so these are the 2 instances we are considering. Now we have considered the same equation at 2 different instances. Suppose at time t1 the reactant concentration is R1, and at time t2 the reactant concentration is R2. Okay, so that would give us 2 equation. Now we'll simply subtract both of this. Okay, simply subtract both of this to get our final equation. So what we have done, we have subtracted this for this. Okay, so that would give us ln R1 minus ln R2 is equals to minus KT1 minus KT2. Now we have again used the you can say this property which says that ln A minus ln B is equals to ln A by B, which says that ln A minus ln B is equals to ln A by B. So that would give us ln R1 minus ln R2 is equals to ln R1 by R2. Here what we have done, we have just solved this equation, put a positive sign here, taken K outside, then that would give us T2 minus T1. Okay, is this clear to you? Right. Now we will just cross multiply it here. That would give us the total equation as 1 by K is equals to 1 by T2 minus T1 multiplied by ln of R1 by R2. Now we are assuming that T2 minus T1 is equals to T. So we are assuming this, and assuming that thing, we brought this thing here, this T here. And one more thing we have done, okay, but one more thing we have done is that it is R1 minus R2. Okay, we have a negative sign. Now what we are doing is we are taking this negative sign out. So it is T2 minus T1. If you take this negative sign out, that would give us T1 minus T2. Okay, this is clear? Right. Now we got this equation. Now this should be positive here. Okay, this should be positive here. Sorry, this should be negative here. Correct. This should be negative here. Instead, here it would be 0. Because R0 is the concentration initially, that is time t1, and also time t1 is greater than time t2. So t1 will be the initial time. So at initial time the concentration will be R0, and here we will have this thing R0 minus, it will be nothing. So let me just cut it for you and write a different and a more correct one. So till this point it is correct, and we have to assume that T1 is smaller than T2. So T2 is greater. Keeping this in mind, therefore K T2 minus T1 we have assumed it as T. That would give us ln R by R, R1 by R2. So this is our final equation. Now we'll take anti-log on both sides. Okay, and how we are taking it? We are just reversing this thing. Okay, that would give us taking minus side on both sides. Taking minus side on both sides will give us this equation. Okay, now taking anti-log, therefore R2 by R1 is equals to minus kt. E to the power minus kt. So we'll see it here. So taking anti-log on both sides will give us R is equals to R naught e to the power minus kt. So this is our initial concentration. This is our initial concentration, and this is our concentration at time t. At time t. So this is the second equation that we got. Again, what we have done, we have removed this ln and placed 2.303 log. So for those who don't know, ln A is equals to 2.303 log A. We can write this. So substituting this value of ln, we can write it further. Ln 2.303 by t is equal to log R naught by R. This is our final equation. So this is the derivation of the integrated first law. Now I've put up an alternative method, a simple method for this. No rocket science, very easy to calculate. First of all, take your differential rate law. Take two limits. At time t is equals to 0, then the concentration is A naught, and at time t is equals to t, the concentration is A. Integrating between limits, this minus dA by A will give us minus ln A is equals to kt. Further, what we are doing, we are subtracting ln A minus ln A naught. Ln A minus ln A naught. Right. Next, what we are doing, we are introducing this minus sign that would give us ln A naught minus ln A. So we have this ln A minus ln A naught along with a negative sign. Now if you introduce this negative sign inside, that would give us ln A naught minus ln A is equals to kt. Again, we have used the same property and we have put this ln A naught by A is equals to kt. So you can see how simply we can just find it by knowing the limit. At two different points, we have to find it. So this is the alternative way to find the integrated rate law. Now let us look at the graphs. So if it's taken the equation, we have two forms of equation that we have seen. The first one is this: concentration at time t is equals to initial concentration multiplied by exponential to the power minus kt. So it is an exponential graph, no issue, but it is having a negative slope. Due to this, we will have a kind of this type of equation. So if you compare it with this equation, that is y is equals to minus ex, you will get x-axis as t here and y-axis as concentration time t. This is the concentration at time t and this is the time. Now if you plot this graph, y is equals to e minus x is the original graph that we have. So we'll compare it with this. So this will form kind of this graph. Now if you look here very closely, you can see that after some time it is appearing that this graph will go parallel to this x-axis. So when it becomes parallel, what is the outcome of this? The outcome of this is this concentration. This is the concentration graph and it is the concentration as time t. So this reaction will never be finished. Okay, this reaction will never be finished because the concentration will never be equals to 0. As according to this graph, this concentration will never be equal to 0. So it will always be there. There will always be somewhat presence of this kind of concentration that was provided earlier. We will get some. It will never go to 100% completion. So this is a very important point, that a first order reaction never goes to 100% completion. Means a first order reaction never completes itself. Okay, is this clear? Right, this is a very important point, that a first order reaction never goes to 100% completion. Next thing you have to deal with is this second graph. So what does this second graph suggest? So according to this graph, we are taking first of all this equation, that is ln AT is equals to minus KT ln A naught. Again, what we are doing, we are comparing it with this equation, that is y is equals to mx plus c. Right. Now on comparing, what do we get? We get x axis as t. So this is our x axis. So this will be equals to t. This is a slope. Though the slope will give us minus k. Y will give us ln AT, and c is the intercept, that would give us ln A naught. Okay. Now comparing it with this equation of straight line, we got that we have x axis as t. What is the x axis? It is t, or time. Okay, this is clear. The y axis is natural logarithm of this concentration at time t. So you can see very clearly that this is y, and it is on comparing both of this, you can see very clearly that this y is equals to ln A at time t, means logarithm, natural logarithm of concentration of A at time t. Talking about the slope, so m is the slope, and in this case we have m is equals to minus k. This m is equals to minus k. And the c we have, which is the intercept, it is equals to ln A naught. So you can say that this is ln A naught. Okay, so this all things are compared, and we can get each of these values if we have this graph and the plots related to it. So this is all about the first order graph. Now we'll move to a special type of reaction, that is of course of first order, but it is of gas phase. So we'll now deal with the pressure. Consider a reaction in which A is going to B plus C. So and it is assumed that it is a first order reaction. Now what is the initial pressure? So since we have assumed that only A was present initially, so B and C both have concentration 0. Okay, and P naught has a concentration of Ag. P naught has a concentration of At. Now we have to consider these pressures as our concentration. For gas phase, pressure is more important. So for now we will just consider all of this, say our P naught or this PATM, all of this as concentration. Now what will happen at time t? Suppose an amount of this A has gone to B and C. Due to this, the partial pressure of A will decrease. So the partial pressure of A will be P naught minus P. Again, B will have a partial pressure of PATM, and C will have a partial pressure of PATM. Okay, so these are the concentration of A, B and C at time t. P naught minus P for A, P for ATM, and P for chlorine. Okay, so this is clear? Clear, right? Now I have told you earlier, this is a first order reaction. What kind of reaction it is? It is a first order reaction. So what can we write about this? We can write the integrated rate law, that is equals to K is equals to 2.303 log P naught minus PA. What is P naught here? Initial concentration. I have told you earlier. What is PA? So PA is the pressure at time t. Okay, so what is this? Say our this PA, it is initial concentration, we can say more accurately. This is your initial concentration P naught, and this is your concentration at time t, or pressure, because in this case we are dealing with gas. So this is the pressure at time t is equal to 0, and this is the pressure at time t is equal to t second. Now we can calculate PA using the total reaction mixture, because we know the Dalton's law of partial pressure. Therefore total pressure P is equals to partial pressure of gases PA plus partial pressure of gases PV plus PC. Okay, what is the total pressure? It will be PA, then partial pressure of gases product PV and PC. That would give us the total pressure. But here we have assumed that the total pressure is this is our PA, PB and PC, and PA, PB and PC are already evaluated. So PA is equals to P naught minus P, and B is equals to P, and C is also equals to P. Therefore P naught minus P plus P plus P. So this is our equation. Okay. Pressure at time t is equals to P naught minus P plus P plus P. Then we know that this P and P will get cancelled. So we'll get it finally as P at time t, pressure at time t is equals to P naught plus P. We can just simplify it further also. So what I have done, I have just added say what we have done, we have calculated pressure P. We have not modified it. We have tried to calculate the pressure P here. So P is equals to PT minus P naught. P is equals to PT minus P naught. Okay. So we got this P. Now we have to calculate PA. And what is PA? According to this, PA is equals to P naught minus P. PA is equals to P naught minus P. So we now know the value of P. So we'll put it here in this place. So P naught minus PT minus P naught. So that would finally give us 2 P naught minus PT. That is PA. So once we have our concentration at time t, we have concentration, initial concentration at P naught. So plug all those values and that would give us 2 P naught minus Pt. So K is equals to 2.303 by T log P naught by P naught minus T. So this is our gas law, but for gaseous phase. It is very important. Okay. Sometimes coefficients are changed and then accordingly we have to solve it. Right? At last, we will see some examples of it. What are the examples of this first order reaction? So the first and foremost example is hydrogenation of ethene is an example of first order reaction. So in this, rate law can be written as rate is equals to Kc2H4. Okay, rate is equals to Kc2H4. Now the most important point I want to make here is that all natural and artificial radioactive decay of unstable nuclei take place by first order kinetics. So if you are given a question like of carbon sampling or finding the age of a radioactive thing or studying the kinetics of this radioactive reaction, then remember one thing, that all the radioactive reaction, whether it is natural or artificial, will always follow first order. So this is the thing. Now decomposition of N2O5 and N2O are also some example of first order reaction. Okay, this is also some example of first order reaction. So this is clear. So you should notice here that although we have a two reactants, but this is, since it is not a elementary reaction, it is a complex reaction. Therefore, maybe the reactant concentration is only dependent upon this concentration of ethene. So this is clear. And the foremost important point is that all decay, all radioactive decay, whether it is of uranium or any carbon 12 atom, so dating of all of this would require our proper order means kinetic study, and while doing the kinetic study we will assume that it is a first order reaction. Likewise, the example here which is saying that we are going from radium to helium plus indium, so the rate now will be written as K into Ra, where Ra is raised to some power that is not defined, but it is 1 and it should be 1 because it is a radioactive decay. Therefore, the rate will be equals to K times radium raised to the power 1. We have another example, that is decomposition of N2O5 and N2O. Decomposition of N2O5 and N2O. So these are also the examples of your first order reaction. So this is all about first order reaction. So we have seen the first order reaction today wholly, but we are left with one topic of the first order reaction, that is a pseudo first order reaction. So if I give you a quick idea of this, so let me tell you. So pseudo first order reaction is something which looks like a first order reaction but is actually a second order reaction. Why? Because the concentration change of one of the reactant is negligible because of the large amount of that which is present. Now due to this reason, although we change the concentration of that second product on which the reactant is developed, it will not change your rate of reaction because of the excessive amount of that present. Okay, because of the excessive amount of that present. So due to this reason, although this looks like a pseudo first order reaction, it is a pseudo second order reaction. Then we will see what is half-life. It is also very important, very important. And we will see collision theory, and at last I will see the Arrhenius equation. So if I talk about the importance of the chapter, mainly you should be good with this integrated law, and secondly you should be good with this upcoming Arrhenius equation because that is also very important. Now we'll see this tomorrow, the leftover part of this first order reaction. Okay, so thank you for today's time. If you are eager, just try to remember, I would say you should try to remember all of the formulas, because having a formula is rather easier than deriving it. But in the back of your mind, just remember the method that you have followed, because it would help in remember the order that you have followed. Okay, so with this I end my lecture. Thank you for today's class.